This is the second part of our presentation that you support exercise number 2. There are 2 topics on domes and elevated water tanks. The definition of a dome is it may be defined as a thin shell generated by revolution of a regular curve about one of its axes. The shape of the dome depends on the type of curvature and the direction of axis of revolution. Domes are used in a variety of structures, for example, as shown, and they may be constructed of masonry, steel, timber, and RC. However, reinforced domes are most commonly used nowadays since they can be constructed over large spans. We apply the membrane theory for analysis of these shells of revolution, and by application of that theory, we neglect the effect of bending moment, twisting moments, and shear. And that is by assuming that the loads are carried wholly by axial stresses. So there are 2 types of thrust, the meridional thrust and circumferential forces, which we use to calculate and to analyze the dome. When you're doing the actual design, remember there's a minimum amount of steel that should be provided on both directions of the dome. Also refer to the requirements of the design of water retaining structures before you finalize and get to your drawing. This is a simple example of an application of the membrane theory to the shells of revolution. The figure shows a typical shell of revolution. That's a shell of revolution that we have referred to here as a circular dome. So you normally consider equilibrium of a small element. You cut a small element and consider an equilibrium of that small element, that the forces along the, that the applied forces. Then you get an equation or a relationship between the geometrical properties of your dome as shown, the different angles, theta, angle phi, the axis of revolution, and these are the directions, n phi, and direction n theta. So for a circular dome, the radius r being acted on by a vertical applied load W, it can be shown from equilibrium that the magnitude of the hoop stress n phi and meridional stress n theta are obtained from the following equations. So these are simple equations which have been obtained. Part of your exercise on this will be to derive this, for example, for a circular dome, where W is the total load on the dome and R is the radius of curvature. The angles can be obtained from that diagram for clarification, and similarly, equilibrium equations can be derived for other types of domed structures. So you can derive for spherical domes, elliptical domes, and so on, again depending on the angles and cutting a small element and checking its equilibrium at the action of loads. The next topic is on elevated water tanks. That's just a figure showing an elevated water tank, a concrete water tank. And most of the elevated water tanks, especially in concrete, are circular, especially for very large capacities. But when these circular tanks have a flat bottom, they are found to be the design is found to be quite uneconomical. Therefore, we go for the so-called intense tank. It's a very special type of elevated tank that is used for very large capacities. And the design components for the intense tank consist of 2 portions, mainly the tank portion and the staging portion or the supporting system. So the tank portion, that is the reservoir itself, consists of the following important elements. There's a top dome which is supported on a ring beam, which itself rests on a cylindrical wall. And the cylindrical walls are supported on a ring beam and a conical slab or dome. At the bottom dome is provided, which is also supported by a ring beam, as shown there. Again, and the conical and bottom domes are made in such a manner that the horizontal thrust from the conical base is balanced by that from the bottom dome. So the conical and bottom domes are supported on circular beams, which is thus supported on a number of columns. And for very large capacities, again, you find the tank may be divided into two compartments by means of partition walls, supported again on circular beams. So the cylindrical wall for an elevated tank are these. You find, of course, the circular wall are generally more economical than those having other shapes, and the tanks are subjected to uniformly varying loads due to hydrostatic pressure, which increases from zero on top at the free water surface to the water to the maximum at the bottom. So of course we have a maximum lateral pressure at the base, gamma WH, which will cause a hoop tension. So you need to work out the hoop tension that will be caused due to the hydrostatic pressure themselves. Then in the circular tank, the lateral pressure causes hoop tension in the wall. The magnitude of that depends on the nature of the joint between the wall and the bottom tank. There are two types of joints which are generally considered in a typical design, a flexible joint and a rigid joint. The difference between the two is that for the flexible joint that is provided between the base and the wall, the deflection at the bottom of the wall is unrestricted, whereas in a rigid joint, which is in which the wall is rigidly fixed with the base, the deflection at the bottom of the joint is not possible. So the upper part of the wall will predominantly have a hoop tension, while the lower part will bend like a cantilever fixed at the base. Thus, a part of the load will be carried by the hoop tension and a part by a cantilever action. So these are two distinctions between the two, the detailing of a joint. So there are different methods that I have just highlighted that have been suggested for design of elevated water tanks. IS 33, that's Indian Standard, that 370 part 1. Part 4 method, there is the Leisner's method, Carpenter's method, approximate method. So for example, in the IS 370 part 4 method, you find the hoop tension bending moments are computed at different heights as well as the shear at the base of the tank. So in this method, we develop coefficients at different heights of the wall from which the hoop tension, bending moment, and shear at different heights are obtained. So that is just short explanatory notes on the cylindrical wall, that's the reservoir. When you come to the staging of the tanks, you find the overhead tanks are generally supported on space frames staging, consisting of RC columns which are braced together by ring beams at the top and bottom, and also at intermediate locations along the height by braces. And this arrangement enables effective height of columns to be taken as the distance between the center of adjacent bracings. Alternatively, the tower itself may be a thin-walled reinforced concrete shaft that can be considered as a cylindrical shell. So we need to consider the behavior of elevated water tanks at the earthquake loading, because this is very critical. A tank is considered having a system with 2 degrees of freedom, whereby a large mass is located at the top of supported system or frame supported system. And the behavior of the tank under earthquake loading is greatly dependent on the staging height and the seismic zones themselves. And in turn, the seismic forces themselves are dependent on the staging height. For example, if you have, an elevated water tank of 300 cubic meter capacity consisting of various staging heights, you can consider various staging heights in a preliminary design. And as an exercise, you can also consider different staging heights or different capacities at different seismic zones and do the analysis and see what the effects would be. So the model is that the tank can be analyzed as a spring mass model subjected to 2 degrees of freedom as per that draft code, relevant code. And the analysis should consider the liquid mass as divided into 2 parts, consisting of 1, the convective and the impulsive masses. Thus, the liquid contained can behave either as convective or impulsive mass. And when you do the analysis, the results will consist of what is the maximum displacement, what is the maximum base shear, maximum overturning moments, and what's the quantity of concrete, what's the amount of reinforcement for different staging heights and zones. For example, if you are doing comparative analysis for academic purposes. So in summary, then the design steps for elevated water tanks is 1, the design should be based on the worst possible combination of loads, moments, and shears arising from gravity and lateral loads in any direction. And you must consider when the tank is both full and also when it is empty. In case of lateral loads due to seismic and wind action, the permissible stresses for columns of the staging are increased as per provisions of the relevant code. So refer to the relevant code that you are using for design to check what are the increments or factors that you need to add to your permissible stresses. However, the increase is not allowed in the design of braces because the seismic and wind loads are primary forces on them. So you note that the increases are in the secondary effect where you don't have the load directly acting. But where you have the braces, the seismic and wind loads are acting primarily on the braces themselves, so you don't add the factors. Then in addition to the entire load of the tank or gravity load, the columns will carry axial loads, shear forces, and bending moments due to lateral loads. So this is to pay a bit of attention to the columns themselves. Then the axial forces in the columns due to lateral loads acting on all parts of the tank as well as towers should be calculated by equating the moments due to lateral loads above the level under consideration to the restraining moments offered by axial forces in the columns. You must also check to ensure that the vertical spacing of rigidly connected bracing should not exceed the limits recommended in the code. Then for staging in seismic zones where horizontal coefficients exceed 0.05, you can consider addition of a twin diagonal and vertical bracings in cases of reinforcement steel in RCC. So in the detailing, you must then again add the provision for taking care of the lateral effects. Then again, for such a tower, all columns should be tied together by a ring beam at the base of the tower. Then a design can never be complete without looking at the foundation for the tower, and the foundation should be proportioned such that the combined pressure on the soil due to gravity load with both tank full as well as empty and lateral pressure is within safe bearing capacity, and in the critical direction, the footing should never lift up at any point. So those are the checks that you need to put with specific reference to elevated water tanks. And that brings me to the end of my part 2 of these explanatory notes. I'll give you the part 3, which will cover tall structures or high-rise structures and cable structures. Thank you.